All right, the very last topic we address in this section about matrix algebra is tying back in solving a system, but now we understand this idea of division, so we can use that in the matrix form. Now, before I start this, let me just mention this is one of those topics that I have to put on the final, that a student can demonstrate mastery of using inverses to solve a system of equations. Let me kind of point out the con here. Unless you've already generated the inverse, this is probably the most cumbersome method of the bunch. Obviously, elimination substitution would be a lot quicker than this, but there is light at the end of the tunnel. So let me kind of go through the theory here, and then I'll point something out to hopefully make this process go a little bit easier. Okay, so what I want to do is I want to take my system and I want to rewrite it to look like this. I want to have a matrix times a coefficient matrix times a variable matrix is going to equal the constant matrix. So in other words, I'm going to rewrite this in terms of a bunch of matrices. And so what I'm going to do, the variable matrix is x and y. The coefficient matrix is just the collection of the coefficients, so 3, -1, -2, and 1. And the constant matrix is just the constants that were on the right side anyways. Okay. Now, this is different than augmented form, so we're not using augmented form and row ops to solve this system. We are rewriting it into this form, and then we're going to take advantage of inverses. Okay, so that said, let's kind of remind ourselves of some theory here. So normally if I said solve for x, you would say divide by a, whatever that is, and divide a by both sides. But in matrix land, we don't have that option. But what we can do is we can multiply by the inverse. So let me set aside a little space here. And if I multiply by the inverse, okay, you got to think back to some properties here. The inverse times itself times the original matrix ends up being the identity matrix times the variable, and this set of numbers over here equals something, right? Well, the identity matrix is like multiplying by 1. So this piece simplifies down to just x, and we have whatever this product is. Okay. So what that means then is if I have the inverse of the matrix, the A matrix, I just multiply it by the constant matrix and I've got my answer. So if A happens to equal 3, -2, -1, and 1, I just need the inverse of this. Okay, now we've talked about how to generate an inverse by hand, but luckily this is not an expectation. So yes, there's an expectation to find your own inverse, but with this particular concept, we're checking that you understand how to use an inverse to solve a system. So if you check back in your notes, we actually found this inverse already. So that 3, -1, -2, and 1, that's the first inverse we actually found. So it's that set of numbers right there. And we went through all the little row ops, and we got that as our inverse matrix, the 1, 1, 2, and 3. So I'm going to copy that down here, because we already did all that hard work. Okay, so according to our little expectation, according to our this process here, to solve my equation, I want to take the inverse, 1, 1, 2, and 3, and multiply it by the constant. Okay, so what that does, how many numbers are in the row? We got 2 of them, so that gives me 2 sets of numbers. Okay, so I want row times column. So row 1, those are the 1s, and row 2 is the 2 and the 3. And then I want column 1, which is 8 and 4. So the 8 goes there, 4 goes there. And then I'm just going to multiply those out. Well, 1 times 8 plus 1 times 4, that's 12. And 2 times 8 is 16, plus another 12, so that's 28. Okay, so that translates into x equals 12 and y equals 28, which is again just another different way to solve a system of equations. So good luck.